Hello, this is Dean Waldo. I'm going to demonstrate another example of a multi-step reaction. And again, I'm Dean Waldo from Pacific Lutheran University. So this reaction is going to be a free radical reaction, and it's a reaction called a pyrolysis reaction, where an aldehyde is heated, and as a result, methane and CO are produced. This is a complete gas phase reaction. And the rate law that turns out that is observed happens to be 3/2 order with respect to the aldehyde. Now, let's look at a proposed mechanism and see if we can apply our ideas of multi-step kinetics to understand and maybe rationalize where this third order behavior comes from. So in the first reaction, we're going to take the aldehyde and actually use blue, but the aldehyde, and it is going to undergo a reaction where it'll have a rate constant Ka, and it's going to form a methyl radical and the aldehyde radical. So in other words, we're just doing an initiation reaction from the ideas of free radical reactions. This is very similar to what you might see in a chain polymerization reaction. The rate law that goes with that, we'll call it VA equals Ka, and that's going to be our aldehyde to the power of 1, and assuming it's an elementary reaction. And then the second reaction we're going to consider is a propagation reaction. So in that case, the number of radicals to start with will equal radicals at the end. So again, we're going to have our aldehyde, and I might just write that a little bit simpler in one line. Oops, let's take those brackets off. And let's have it react with the methyl radical. We'll call this Kb, and out of this we'll end up getting methane. In other words, a proton left the aldehyde and is attached now to the methane, and we're left with the radical that's of what is left from the aldehyde. And this rate law will be Vb equals Kb. Now this will be second order, and we'll put it in terms of the radical and the aldehyde, CH3CHO. So that's a second order reaction. And let's have one more propagation example, or step in this reaction. We're going to take the remaining radical from that previous reaction, the part of the aldehyde, CH3CO dot, and that's going to undergo just a basic unimolecular decay. We'll call this rate constant Kc. It's going to again form another methyl radical, and in this case CO, which, just as a reminder, is one of the products of this reaction. And the rate law for this elementary step is going to be Kc, and then just concentration of CH3CO dot. Since this is a free radical chain reaction, we have to terminate the radicals at some point, and so we're going to use the following as a termination reaction. We're going to have 2 methyl radicals come together with a rate constant of Kd forming ethane, and this is going to be have a rate law of Vd will equal Kd, concentration of the radical, methyl radical squared. So at this point, we have defined all of the elementary reactions. We've defined the elementary rate laws, and now let's see if we can apply the steady state approximation to intermediates. So let's identify the intermediates we're going to look at. One is going to be the aldehyde minus the proton, so it'll be this one, and also it'll show up here. We'll also apply an intermediate to the methyl, the CH3 radical, which shows up here, 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 and in the last equation twice. Do note that there is one other radical that's produced, and I will indicate that with this yellow, and that's this one over here, but we're going to essentially ignore that one because it doesn't go on to react in this particular mechanism. So we're going to focus on the methyl and the aldehyde minus the proton. So let's look at the aldehyde minus the proton first. So I'll slide this up here. So let's ask ourselves what can change that concentration. In other words, what's going to change this rate? And we see that in reaction 2, that reaction will increase the concentration. So if we say plus Vb, and the only other reaction that can affect it is C, and that's going to decrease the concentration, so we'll say minus Vc. Now we can apply the steady state approximation and say that this rate is going to equal 0. So therefore, I think it's always good to develop any relationships you can with these variables before you start replacing the v's with what they're equal to. So we'll say Vb equals Vc. Now the other intermediate we're going to look at is the methyl radical, CH3 dot. So what can change this concentration? And it turns out all 4 reactions can change it. So the first reaction, Va, is going to increase the concentration. Vb will decrease it, so we subtract that. Vc will increase it, so we add that. And last but not least, we're going to look at the last reaction, which is D, and we're going to take 2 methyl radicals out for every reaction, so we're going to have twice that rate. And again, here is where we'll apply the steady state approximation. And this is where we can make use of looking at these relationships before we replace things. So notice that Vb equals Vc. So what if we replace Vb with Vc? So we can replace this as Vc, and therefore these two will cancel each other out. And we're going to be left with Va minus 2Vd equals 0, or Va equals 2Vd. So we can take this relationship, in this case, let's replace Va with what it's equal to. So up here we'll say Ka, concentration of the aldehyde, CH3CHO, is going to equal 2 times the rate constant for D times the concentration of the radical methyl group squared. And in this case, we can now just solve for intermediate, at least one of the two intermediates. And as it turns out, this is the only one we will need, but that wouldn't be known unless you had worked through the problem. So let's go ahead and solve for this. So I'm going to say that the concentration of CH3 is going to equal, so that just means I've got to divide both sides by 2kd, and then take the square root of both sides, and I'll end up with Ka over 2kd to the power 1/2 times the concentration of the aldehyde to the power of 1/2. And let's just remember that that is the radical. Okay, we can also go back and set VB equal to VC and solve for the aldehyde minus the proton, that radical. But as it turns out, and we'll see momentarily, that turns out not to actually be very useful in this particular case. So let's now ask the question, how can we describe the overall rate of reaction for this reaction? So let's focus on methane, and let's calculate the rate of production of methane using this multi-step reaction. So if we come back down, let's write the derivative of methane with respect to time. What is going to influence that concentration? So the only place that the methane shows up, let's use this color, is in reaction number 2. So let's say that d-methanol, or methane dt, is going to equal VB, and that's going to be positive. So if we substitute that in for its values, it'll be Kb times the concentration. Let's get this straight, the aldehyde times the methyl. So that'll be CH3CHO times CH3 radical. But we now have a description for the radical concentration, so we can replace that. We'll say Kb CH3 CHO times Ka over 2kd to the power 1/2 times the concentration of the aldehyde to the power 1/2. So note, we can combine the constants and we can combine the aldehyde, and as it turns out then, we have a description for the rate law that is in terms of aldehyde to the power of 3/2. So let's just rewrite that. dCH4 dt equals bracket, and I'm going to move the Kb inside the square root just to clean things up a little bit, so that means I'll have to square it. So I'll say Kb squared times Ka over 2kd to the power 1/2 times the aldehyde concentration to the power 3/2. And here we have our answer. Note that we are using this mechanism, and we've applied the steady state approximation, and indeed we found that the order with this particular multi-step reaction is to the power of 3/2, or the order is 3/2 with respect to the aldehyde, which is indeed what's observed. So that would give us good confidence that this is a pretty close, if not accurate, representation of this mechanism. Thank you. Have a good day.